Hey there, welcome back to COG 376, Computer Models of Language Representation and Processing. Today we're going to talk about working with text in a general sense to sort of set the stage for any programming we get up to in the near future. So, let's just walk right into it. Setting the stage. Before we get dirty with genuine programming skills that I've promised, let's talk about what kinds of processes are we actually going to be implementing? Sort of the why and the what and the how, or perhaps less the how, more like how what we will learn to do becomes a piece of these broader processes and where it sort of all fits in. So far, we've talked about some pretty interesting things that natural language programs can achieve. If we recall our friend GPT-3 that takes text as input and then processes it to make text outputs that are sometimes pretty amazing. For example, here's some examples of what GPT-3 can do. So given the question, when counting, what number comes before 100? It can answer 99 comes before 100. When counting, what number comes before 123? 122 comes before 123. All right, what about what number comes before 1,000? 999 comes before 1,000. So we're seeing how these are not the most wild examples, but we're seeing how it's able to take the sentence that is given to it, process it in some way that really gives it kind of the understanding. We've given it context, we've given it counting, when counting, what number comes before 100, right? Not, in my social security number, what number comes before 100, right? And it's able to take that context. It's taking the question, it's able to break it up, it's able to look up what this series of numbers is and find the answer, and it's able to spit it back out in text. How is our big question? How is this happening? Well, that's a huge, extremely involved whole research program going on to make this stuff happen. But where do we begin, perhaps, is the better question. Well, we begin by learning what it is to process text. So in any process, you're going to have some kind of input and some kind of output. Sometimes that output is actually internal to some other broader process, right? So the process of memorizing a phone number, you don't actually need to say it out loud to consider it memorized, right? You can just look at it and internalize it into some memory storage in your brain, right? That is a process. It has an output, but that output is hidden from the world. Whereas with, generally speaking, text processing, well, the input is going to be text, of course, but the output could be text in various forms. Sometimes it's internal data structures that we'll use for later use, and sometimes it's external, which is the natural language that is produced again in the form of text, right? So we feed, I'll go back real quick, we feed it this string at the top, when counting what number comes before 100, and it spits us back out something that resembles human speech, right? 99 comes before 100, and so on. So that's the idea. This is what we're trying to get at with understanding what are we doing when we take text and we try to do language modeling stuff with it. To make it a little simpler, so this will have similar things to do with the example we just used, but Eliza. Eliza is an old text chatterbot, one of the very first ever made. We'll talk about it in many ways over this course. So Eliza is a system that's able to take words that you have said to it. It's able to sort of look for certain patterns in your sentence and make sense of it. For example, here, what's your name? Amit, right? Hi, I'm Eliza. What do you want to talk about? Can I talk about my problem? Sure. Due to ongoing exams in college, I have a lot of stress. Please relax a little. Sleep well. Thanks for your advice. No mention. Bye. Bye and keep in touch. This is a little silly compared to most of these examples, but you can see that it's able to respond in certain ways. It almost Eliza takes the text that is handed to it, and it's not a real person, right? It's not thinking about what it should say to you. That's already been done in many ways. For example, how does it come up across its third line? Please relax a little, sleep well. It wouldn't have said that if the user hadn't entered something that it could seize on, that it could find a particular word that it can respond to with actual decent advice, right? In this case, exams in college is probably not it due to that's all kind of extraneous. The real key of the sentence of the thing that was admitted by Amit was, I have a lot of stress. Stress is the thing that Eliza is responding to here. And you notice that Eliza didn't mention exams. Eliza didn't say, oh, don't worry about it, you'll probably do well, right? That's not what Eliza is made to do. Eliza is capable of seizing on very specific patterns that it knows things about. And when I say no, I need to be precise and say it has data stored that it can use to look up a useful response for the concept of stress. So let's look at another, this is a more classic conversation with Eliza. This is one of the first conversations ever had with it. It was a secretary for the developer of Eliza who had a little conversation with it. It was, men are all alike. Oh, in what way, Eliza says. They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. Your boyfriend made you come here. Just mirroring, right? Not really adding something new, but it's able to take something that was said to it and mirror it back, which, to be quite frank, is a useful technique in therapy sessions. That's what Eliza was originally made for. I should have said right up front. But Eliza was made to simulate certain aspects of therapy so that you could give people this talk therapy experience that it's not going to be complete, but at least it's something, right? It's an automated way. Let's continue. So he says, I'm depressed much of the time. Oh, I'm sorry to hear that you're depressed. It's true. I am unhappy. Do you think coming here will help you not to be unhappy? I need some help. That much seems certain. What would it mean to you if you got some help? Again, some help, right? I need blank, some help. What would it mean to you if you got blank, some help, right? Perhaps I could learn to get along with my mother. Tell me more about your family, because it saw the word mother. And it continues like this. This is an example of how Eliza is doing some really fun, interesting tricks to look like it understands natural human language. But I promise you, Eliza is just a program. And honestly, by today's standards, it's not a very complex one. It's quite simple. Let's pick apart a couple of these lines and figure out what we're working with here. Well, my boyfriend made me come here. Your boyfriend made you come here. Okay, so there's a couple of things we can see here. It's definitely mirroring something, right? How is it mirroring? Well, it has my, and then it has some sentence that comes after it. The rest of the sentence. It is a sort of a distinct clause that seems relevant to the person who's saying it, right? Eliza is able to engage in this mirroring. It could probably do it pretty much any time, but it does like things where the user has referenced itself, himself, herself, right? So the user says, my something important to me. So it says, oh, you're something important to you, right? It is parsing the text, breaking it up into these things. Now, as I'm saying this, I want to be clear. It's not saying, I understand that this is important. It's more something in the text code has said, anytime they reference themselves, you could potentially do this mirroring thing. You might just randomly do it. So it does the mirroring, right? Your boyfriend made you come here. That's a prompt to get them to go on, right? So then she does, and he says, I'm depressed much of the time. Well, that's an important word to a therapist. Depressed. That's a key word that has been seized on. Now it also seeing that this is her that it's talking about and not someone else. I'm depressed. Now Eliza can say, well, I'm sorry to hear that you are depressed, right? So Eliza is doing something interesting here, and it was constructed to do this task, so that's why it's okay at it. It's not just a random chatbot that's been trained on random things from the internet. It's someone trying to achieve a useful outcome for its users, right? So let's break down Eliza's kind of basic ideas. What is a system like Eliza doing? It's taking the text as input. It's processing it somehow. Okay, what does that involve? Well, it's definitely segmenting it into words at least, right? It's able to seize on specific things like depressed, mother, references to self, right? And it looks for patterns. It looks for specific stuff in there. And it's able to definitely look things up to make sense of the meaning, right? It knows the word depressed has a different set of reasonable responses than the word mother. It wouldn't say, I'm sorry to hear that your mother, right? That wouldn't really mean anything. So that's not included in Eliza. And then in the end, it produces a matched output that, for all intents and purposes, is more or less handcrafted. It's just included in a large set of things that Eliza is allowed to say, and also text that it's allowed to fill in variables for, right? So the idea of saving variables from Eliza, putting them into storage, cross-referencing where they might live elsewhere, and pulling them out again. So in Eliza, we see this example of how some text processing comes together to allow us to do some interesting things. And there's tons of examples, right? GPT-3 does a lot more than Eliza does. Text completion on your phone does something similar in terms of the amount of effort it's putting in, but it does it in a different way. It's doing it based on the things that you have historically typed into your phone, not just matching patterns, right? So what we'll talk about today is a way of kind of a broader way we can situate questions about, okay, what kinds of processes are these that we're talking about when we are working with text? So we'll use the two-axis approach. So when you are modeling text-based language on a computer, you can consider two separate axes, sort of a grid system, right? On axis one, you have to consider what is the goal of your design of your system, right? What are you actually trying to achieve using your text-based processing system? You're not trying to make a general reasoner, unlike the GPT-3 people who are attempting to do that, although it has its limits, right? Even though it's pretty impressive. And then on the other axis, you have the question of what is top-down and what is bottom-up. Top-down is something that you've maybe designed yourself altogether from rules that we know about language, from specific patterns that you're looking for, right? Eliza is very top-down. It's not learning from the environment. It's not looking at scores of text communication to figure out what it should say. It's just a system designed carefully to respond in specific ways to text that it sees. Whereas a bottom-up approach is more about things like machine learning, letting something study a million, a billion, a trillion documents and figure out what kinds of processes, what kinds of relationships it can pull out of that kind of study. So these are the two different axes, right? So what are your goals? That'll shape how your system works and what it does and what it includes and what it excludes. And then top-down versus bottom-up is more of a flavor. What kind of thing are we doing here? So we'll talk about all these. We'll make them more explicit. So on axis one, the goal, right? How you deal with text is going to depend on what you want to do with it, right? You're not necessarily trying to make a system that can read text and just generally know exactly what it should say on the other end, right? For example, keyword-based search, right? When you are searching in Google, in a search algorithm, in a search system, it doesn't super matter what word order you use because there's no such, it doesn't care about where things live in sentences unless you use the quotes. So, I mean, that matters. But specifically keywords, right? I could type car windshield repair just as easily as I could type windshield car repair or repair car windshield. It's going to turn up all the same results. It doesn't have any concept of order. Word order is meaningless for keyword search. But then you have something like Siri, right? These well-specified domains where we know exactly what kinds of things this system should be able to return, because we know Siri can only do things that are local to its phone, or rather, it can only go through systems and apps that are local to the phone. So you ask Siri, hey, what's 5 plus 10? It actually does handle it. It does understand 5 and 10 and the question what's, right? So it's able to look at these predefined structures in the text. So the word order does matter. You couldn't put 10 plus 5, what's Siri, hey, right? That Siri, it needs to have hey Siri first to understand that you're speaking to it. Oh, there's my Siri. Oops. Yeah, well, I didn't get that. Could you try again? No, it's okay. It's okay, Siri. Oop, back. So the idea is that in certain domains, you will be very specific to what task is available to the system. ELIZA is like this. It's a highly specified domain. It doesn't have a general problem solving ability. It just has, I know the exact kinds of patterns I can pick up on. And if I don't know something, I'll just hedge. Sometimes ELIZA can spit out more sort of a filler sentence to get you to just say something else because it doesn't really know what to say. Let's look at Siri again. So Siri has some knowledge of the world, and it has a little bit of linguistic knowledge. But here's a case where it misses the context entirely. What is the cost of a train ticket from Sydney to Brisbane? The answer is about 28.8 quadrillion kilometer US dollars squared. What? So what Siri did with this was it tried its best to chop this up into a meaningful set of things it could look up using Wolfram Alpha, which is a sort of a knowledge engine online. Siri didn't know the answer to this. It didn't have it stored on itself, right? But it could go to Wolfram Alpha. The problem is it malformed the concepts involved. It thought it was talking about the train, the movie. So it was like, what price? The cost of the train? Well, that's box office value, something. And then it's like, wait, you want me to go from Sydney to Brisbane? That's distance. So I've got the budget of a movie times the distance, 28 quadrillion kilometer dollars. That's a unit that has some meaning in the technical sense. You can combine units like that, but what does that mean for? I'm trying to get to Brisbane, right? So Siri flubbed it. Siri dropped the ball. So this kind of illustrates you have to kind of understand what your goals are because you can't guarantee that your system is going to have general applicability. Now the question is, hey, can we try to get to true understanding of language? Well, let's explore that. So consider this. Time flies like an arrow, fruit flies like a banana. What do you need to do to understand this sentence? Now, if you haven't caught it yet, there's two alternate meanings here, right? Time flies like an arrow, right? Time is the object, and it flies similar to an arrow. Whereas the back half of the sentence is the same construction, but the context means you're going to parse it differently. Fruit flies enjoy a banana, right? Fruit doesn't fly like a banana. It's a play on words. It's word play. It's almost a joke, not quite a joke, somewhere between normal language and a pun. But it's this interesting case where to get the joke, you have to figure out, there's an alternative, right? There's something that is ambiguous here because one of these doesn't make too much sense. I have to check with the world and my understanding of semantics to say, Fruit doesn't. What is flying like a banana mean? That's nothing, right? So the question is, what are you doing to get the joke, right? What are you doing to disambiguate this and see, oh, haha, that's kind of silly? And then the question is, what would make a computer different from you in the way that you are able to disambiguate this sentence and get the joke? True understanding is tricky. You have to assemble meaning of a phrase or sentence from its meaning components, right? But then you have to go through these other steps, right? So you have to use your knowledge of language, your knowledge of the world, and whatever context is provided to you. That's a lot of really diverse, broad information that you could bring to bear on the sentence parsing, right? Then you have to get a representation of your knowledge and start to engage in some kind of reasoning to extract, like, oh wait, there's multiple ways to take this. And finally, you understand, right? If I could just make a computer do all those steps, hey, that's AI, baby. We can go home. It's over. We've done it. Right? Well, yeah. I mean, that is too much. That is too much to ask of any given machine. And even our friend GPT-3, it is still extremely limited in terms of general understanding. Because general understanding involves so much processing of various things. Like you see here, your knowledge of language, your knowledge of the world, context, which can be, all of those can be really shaky. They can be amorphous. They can be things that are difficult to pin down. How do you encode all knowledge of the world in a way that makes sense for usage in processing language in a computer? You don't. Or at least if you're trying to make something useful, you don't try to do that as your first step. So instead, we opt for something closer to simulated understanding. We don't expect a computer to understand everything we give to it. We need it to understand sort of a limited version of it, a small scale version of it. Some might say a micro world version of it. Because by that metric, we can then fake understanding to still get a useful result. For example, machine translation, where you give Google a sentence and it says, oh yeah, I'll take this from French to Spanish. Sure. It's auto-translated, right? A normal human being, to understand that, would have to use their deep understanding of both languages to really give you a processed understanding. This is why Google doesn't always fit the bill when it comes to processing language, because it's not just literal word for word translation. Sometimes there's cultural references or knowledge or sort of euphemisms or turns of phrase or whatever, you know. There's a lot of information behind an understanding of a sentence that would need to come to bear. But that said, so what, right? If I can get Google to translate 80% of all sentences that are just factual, like where is the bathroom, that's great. That gets us there in most cases. Conversational agents like Eliza we talked about, there are tons of others, and sometimes they are designed for things like helping you get through your Grubhub help menu, right? We may come back to that one in the future. Conversational agents are, they don't need to understand language. They just need to sort of get us to a place where we feel like we've been heard and some system has processed what we're talking about. And then synthesis and summarization, right? So you might, on occasion, on different forums and sort of different social media places, you might see automated summaries of things. You see this in Google too. An automatic summary that says, hey, I've processed the document and I think this is the quick version of the document, right? You know it's not going to be correct. It's not going to have nailed it, but at least it gives you a quick eyeball version of, okay, here's what I think is in there, and this system has probably done a decent enough job to get me, should I look into this further, right? So these are all the different ways that you can trim down what we mean by the word understand and use it towards something useful that is still, not quite real language, but still useful. And just as a side note, you might even pass the Turing test, right? If you're not aware, the Turing test is the idea of, oh, can I make a computer system capable of producing language that is confusable with a human? It's not necessarily that it looks human, it's just that you might be able to fool somebody in thinking it's the human in a case between two. But under the hood, we still will always know that anything that we're making for the most part is an imitation of language understanding. It's not the real deal. Have you heard of Watson? Remember Watson? It is the robot that went on Jeopardy and it did pretty great. It was a system, an interconnected system of knowledge and language processing abilities. It's able to take the questions, it's able to follow the rules of Jeopardy and take the answers, right, and form the answers in the form of a question. But it also is able to know things, right? It had some probabilistic way of guessing which thing was the actual thing it was supposed to say. It had all these processes, right? But in the end, those famous in the field of artificial intelligence, like John Searle, told the Wall Street Journal in 2011, Watson did not understand the questions, nor its answers, nor that some of its answers were right and some wrong, nor that it was playing a game, nor that it won, because it doesn't understand anything. It is just a chain of dominoes in his view. It is information came in, it was chopped up in particular ways, it was turned into text, it was turned into knowledge, it was turned into knowledge that required some kind of hole be filled, and it consulted a database of knowledge that it could use to try to fill that hole. It didn't care if it won. It didn't know that it won. It didn't matter to it that it was playing the game. It was just a system doing the thing that it was designed to do. It's a little sad to think like, oh man, like Watson was kind of a cool experiment. If you want to see it play, go check out that YouTube video. But that's the case, right? It is not a person, right? At least not yet. Where there are some philosophical questions about where cognitive science is heading and AI, but for now, the way that we look at these things, we have to understand that under the hood, it's just cutting corners. It's not a deep and true perfect representation. I couldn't ask it for advice on my taxes. I couldn't ask it for a tip on my marriage, right? I'm not married. That's a silly example, but Searle's onto something. So that's the idea. When we're considering this first axis, we start with the basis that we can't expect computers to just get it, right? The computer's sense of understanding language is always going to be simulated. So even GPT-3, as I said before, it's marketed as a general text transformation algorithm, which is very cool, but it only works within certain parameters. It is getting more complex every day, but we'll leave that on the side. Maybe a version of this course in a few years will be eating crow, but we'll see. So the main point is the form your program, your process, and your model, all these kind of overlapping concepts deal with the form in which they deal with text-based language. That will take a different shape depending entirely on what you're trying to do, right? For example, language translators are going to be wildly different in their structure compared to virtual assistants. They're just not doing the same things, right? A language translator is taking language from one natural language and converting it into language from another. It does it imperfectly, but it does it pretty well. Whereas Siri is taking language from its user and converting it into actions or answers to questions or etc., right? So that's axis one, the goal. What are you trying to do so that we can understand what we need to simulate from language to get there? Axis two. Now this is a little more theoretical, but it has huge application, points of application. So when your system is your text processing system, it might be more top down or bottom up. This is a common refrain in cognitive science. There are other ways to frame this debate, but more or less, top-down is the idea of using known structures and rules to match patterns and transform information in ways that we already understand. So, ELIZA, we already know what kinds of patterns we want to be able to seize on as the therapist role, to be able to say, depression, that's a very important word to this thing that we're doing right here in the chair, right? So that is a top-down approach. We have coded directly into ELIZA the ability for it to notice things that are relevant to most conversations with a therapist. On the other end of this spectrum is bottom-up. This is where you use processes like machine learning to let the system pick up features of natural language and build some kind of understanding, which we may or may not understand ourselves or even agree with. So let's pull some examples down of these. So for top down, you have things like symbolic processing, right? So symbols are these clean, reduced representations of other concepts. So the letters and the words on this screen are an example of symbols. You understand them because you're able to tie them to some kind of meaning and use them, right? As you humans are so wont to do. But this is great. It has an excellent mapping to language processing because, hey, language is symbols. That's kind of the whole deal, right? So this is a top-down approach. We are designing by way of writing code that uses the properties of things like sets, lists, logics, rules of grammar to capture some of the known structures of language and then use them in prescribed ways that we already know sort of what the parameters are. And this is not, these are not panaceas. They have their uses for sure, but they are very kind of specific, right? For some tasks, it's easy to produce and you can correct them easily by saying, okay, what are the edge cases? Let me try different things, all this kind of stuff. This is all good. This is great. This is still useful. You can build very robust language models using symbolic processing. More on the other end of the spectrum, right? We are talking about an axis, so things can kind of lean both directions. Let's look at machine learning, right? Machine learning is letting a process run that scans text, extracts its statistical and probabilistic properties as a way of understanding that text. So this is the idea of letting you're not building the system to do very, very specific things. You're building it to learn, right? So the bottom-up approach, right? The designer takes a back seat and it lets the program kind of learn all it needs to from the world on its own. It'll study hundreds, thousands of documents to sort of figure out, okay, what's the regular structure of a document? And maybe I can produce something like that. And the cool thing about machine learning is that it usually gives pretty good performance pretty quick. If you're building a system that you need it to do a certain kind of, so for example, translation, 80-20 rule applies here as a good old friend of learning in many cases. 80% success in 20% of the time, right? Whereas the rest is sort of diminishing returns. And it can become quite resilient. It can be really, depending on how complex you allow the machine learning model to become under the hood, it can learn to be pretty general. It can learn a lot of information that you could never hand code in it. Because you're allowing it to study a trillion things that you could never read on your own, right? Now, there is a debate, as is so often in academe. There's a push and pull. So which of these approaches is more appropriate? Should we carefully craft systems using this top-down symbolic process, these things that we understand already? Or should we let them run wild and extract everything they can from the world, right? The world is filled with text data these days. In fact, it's one of the most prominent ways of communication, especially these days. So this is the idea. This is sort of a tension. And there are different ways to frame this. So there's theoretical issues of, hey, man, is language actually like this, right? Can you learn language just by turning an algorithm loose and letting it look at all the words, right? Is that actually going to give it language capabilities? Or is our actual current understanding of language robust enough to do it all in the top-down way? Do we actually know every process of language? Are there things that we're leaving on the table by ignoring the bottom-up data processing type thing? Of course, the answer to both of these is yes and no, right? So, but moving forward with the same questions, there are practical issues too. So machine learning models can really become biased pretty easily by whatever data they are fed. And they can overfit the examples they've learned based on. So, those are kind of the same thing. There is a way of biasing the system based on what data it has absorbed, right? And worse than the fact that they can become biased, and sort of the compounding issue with them, is that they're opaque. A machine learning algorithm has learned a whole bunch of numbers that it multiplies different inputs and outputs by to come up with its answer. A human just kind of looking over those numbers, that's nothing to us. We can't really make sense of just a big whole bunch of multiplicands, right? So it's hard to interrogate what the algorithm actually learned. It becomes very difficult to do that. So even if we know it's become biased, it's difficult to understand how it's become biased. So that is, that's a pretty rough patch for machine learning. It means that we're just kind of trusting that it's going to do everything the way we want it to. But then, on the other hand, top-down approaches can be really limited. They're very narrow in scope, right? And they can really screw things up because when things kind of fall outside of their scope. Consider series catastrophic response. So, for our purposes, these debates are fun to ponder and they help guide future theory and development and all that. But ultimately, I will tell you, as is often the case with these theoretical debates, the pragmatic answer is use a bit of both wherever it's useful, right? Sometimes a machine learning approach is going to do something cool for you. Sometimes it really won't. And sometimes you can combine them, right? So you could have something learn maybe the statistical properties of, how often is when so for ELIZA, we could feed into it the ability for it to learn from all the things it's heard, right? So it has a structure, but it also knows, when people say the word depressed, they actually mean sad, because it's become quite common in common language, the current era language, to depression can be a very serious clinical thing, whereas general sadness doesn't necessarily equate with that. So self-diagnosis could be a question that ELIZA could try to answer by training, right? But we don't necessarily need that either. That's not what ELIZA was originally designed to do. It's not the thing it's trying to achieve. So just because it can be done doesn't mean it needs to be done. So anyway, in this debate, this is more about categorizing where you're at. And, you might not want to lean all the way in one direction. So we can identify whether we want to use these prescribed symbolic processing approaches or more data-based machine learning approaches. There's some debate as to which one is most appropriate, but they're both useful in different ways. So that, I hope, kind of helps to frame the space, at least, right? We have axis 1 with sort of determining what are we actually trying to do? And axis 2 determining, so what is our, broadly speaking, what is the way that we are doing it? So, okay. Let's walk through an interesting example process of how text can become something a little bit more than just raw text, right? It can become some form of understanding. And that could be relation parsing. So this is the idea: we want to take a sentence and turn it into a relationship. What does that mean? So it's a sort of ontological thing. It is the idea of, if I say some sentences are strings, that implies some kind of knowledge connection, a two entities that are related in some way. So for example, the object being some sentences, the relation being are, this one directional thing, strings being the subject, right? So this is natural language in a sentence that may be converted into this other structure, right? It's a structure that implies some kind of knowledge about the world, right? If I know this thing, that some sentences are strings, then I can use that. That can be useful. That's a better form for general knowledge, right? So how do we do this in a computer? How do we get from point A to point B? The A being a string of text that's been fed in, to B being this relational structure. Well, we'll follow this. This is not necessarily what we will be building. This is a little more complex, but this is the idea. So I hope it can illustrate some things. So first, we would have to tokenize the text. That is, split it into meaningful tokens. Then we might do something like tag the parts of speech and the morphologies, so some basic linguistic tagging. We might need to name, to recognize named entities. So that's the idea of, if you say the Washington Monument, that is a proper noun, right? I need to know what that was, what kind of thing that was. Then we would parse the sentence structure a little more deeply so that we could then pull out the roles and relations, the roles of different parts of the sentence in the relations of the object-subject relation connection. So corenlp.run is a little website that framed this around. You could go there. It's fun. You can put sentences in that will do this stuff with them directly. So let's walk through this process, right? I hope I can demystify a little bit of this by, it seems crazy. Oh my goodness, how could we get from some sentences are strings all the way to this form? Well, let's walk. So tokenization. This is where we take a string of text and break it up into units of meaning, aka tokens, and in this case, they would be things like sentences or words, right? So string, if you didn't know, is a data type meaning a sequence of letters. It is a basic form that text takes in computers. You must know and understand what a string is. I'm saying that to you as a person. You must know. So keep that in mind. But then sentences and words, the tokens that we're talking about, are meaningful concepts in language, right? So these are the meaningful chunks. You don't split up a string that contains an English sentence. You don't cut words in half. You cut them on the white space, right? So the idea is that these tokens are strings themselves, and they're a little more bite-sized, and they're easier to analyze both separately and together. We can choose how we analyze them as opposed to having one big block of characters in a row. So, for example, this string of text will become tokens, splits up into this and string and of and text and will and become and tokens. Even the period should be cut off the end there, but that's the idea. So taking a big block of text string and turning it into meaningful units. Next step of this process is tagging. So you take each of those tokens and you look up what part of speech it is. Are these things nouns? Are they verbs, adverbs, punctuation, determiners, all these fun things of the syntax part of speech things, right? And you also might need to disambiguate when one word could fill multiple parts too in this step. On top of this, though, we can look at the morphs, right? So the different forms a word might take. So things like adding the S at the end, that implies plurality, or perhaps you might have a verb that implies an action that requires both subject and object, or only one, right? But you can see we're beginning to access some of the meaning of these words. They are sort of magically becoming, from just a row of characters, a row of letters all in a row, they're becoming things that might mean something. So here we have an example from the site. The quick brown fox jumped over the lazy dog. The is a determiner. JJ, I guess that implies these are adjectives, right? Noun for NN, VBD is a jump. Is a verb, it's a jump. Over, that's the idea. So you can start to tag out what parts of speech these things come from. Then we have a third step that it's relatively short, but it's to help disambiguate some things. This is a quick step to fill in confusing words to see if they refer to a known real world object. So proper nouns, right? People, places, objects, organizations. You might need to recombine some units, right? So some of the tokens might need to be put together from step one to make sense of them. I threw in a sample sentence that's pretty ridiculous. The quick Mr. Rogers jumped over the entirety of Philadelphia, right? So this step, we see that Philadelphia is correctly caught as, oh, that's a city. I can fill in city-like things, like place, for what this is. Whereas Mr. Rogers is a person, implying it's a noun. Although it has missed, this particular algorithm has missed the Mr. part, right? So it leaves this Mr. just kind of hanging loose. But it still recognizes as a person, so that's useful. Okay, so now we've really filled out the sentence and we've kind of made sense of what kinds of words are available in the sentence. Now we can reparse its structure. So thankfully, this is a pretty well understood process, right? We parse out the sentence diagram, and then we can use that to start to get at, using the grammar rules, and you can start to get at the dependency between words in the sentence, right? So which things modify which other things. If we have these two nouns, fox and dog, and all this other stuff going on, how do we form the relationship? Which things are referring to which things, right? So dog is getting the lazy, right? And over is sort of not clear. It's in there somewhere. Jumped, though, is certainly the pivot point. And then we have the fox, which gets all of the quick and the brown and all that. So that means that we have a sentence that has sort of one pivot. There might be one relation in here. So now we can get to the step of role and relation extraction, sort of the final mode that we're looking for here. So we will label the roles each noun plays in the verb connection. And then from that, we can construct the relationships involved in the sentence, right? So this is a huge part of turning sentence structure, the syntax, into more meaning, right? A meaningful thing, a relational element. So the quick brown fox jumped over the lazy dog. The subject, the quick brown fox, jumped over the relation, the lazy dog. That's knowledge. That is a little piece of knowledge that comes from this sentence, this string of letters. So, looking at the process top to bottom, we see how we can take this sentence, break it down, and look at its individual pieces, give them labels, give them understanding from a database of knowledge about which words are which things, and then we can build a new piece of knowledge out of it from this string of text. It's pretty useful. You could use this to build a whole database of knowledge. So then when asked a question, what jumped over the dog? It could maybe fill that in. It could figure it out. It could look up, the quick brown fox, most likely. You didn't say lazy dog, but you did say dog. And something that was jumped over it was the fox. Okay, so that's the idea. I hope this helps to kind of pick apart and disambiguate. It's showing us how you can go from just a primitive data type like a string, that just the raw idea that computers can have text on them, and process it forward into something a little more abstract, a different representation, right? All using fairly straightforward steps. We don't know everything about every step here, but none of them seem mysterious, I hope. Completely mysterious, at least. I don't know all the adverbs and all the different rules of grammar and everything. I'm no language genius, but these things seem doable, right? From just looking at them, figuring out, okay, I could apply tags to a thing. Oh, I could relate things to things, right? And in the end, we come up with this new representation that could be useful in different ways. But let's look at how this system could still flail. It's impressive the way it does things, but it's not perfect. So let's look back at our example. Time flies like an arrow, fruit flies like a banana. Did this NLP system, the core NLP project, Did it get the joke? Is the question. Well, let's see. Time flies like an arrow. Fruit flies like a banana. We could jump down to the bottom and figure it out. Let's see. Flies like an arrow. Ooh, they look like they're kind of identical. We know they should be a little different, right? So, yeah, where'd they go wrong? Well, right at the start, we can see it's saying flies like. So flies, it's still tagging as a verb, and in is like is sort of this relational bit. So this is not accurate, right? We that's how it works for the first part. Time flies like an arrow, but flies in the second half should be a noun, right? Fruit flies. Fruit should be a modifier of flies, the noun, and then like should be the verb, right? So in the end, this second half, it's wrong. It didn't get the joke. It has formed the same relational structure for the first half of the sentence as the second half, when it should be fruit flies is the subject, like is the relationship, the relation, and the object should still be banana. So, it didn't get it. That's okay. You're still really impressive, core NLP. So, taking this, just thinking forward, what are some other tasks natural language we could do with natural language techniques like this, working with text? Word sense disambiguation, so figuring out what sense of a word someone was using, that could reach into some of this grammatical understanding. Co-reference resolution, so which things are being co-referred in sentences. Topic segmentation, so figuring out what a particular block of text might be, what might the topic be. Right? Summarization, we talked about a little bit already. Discourse and sentiment analysis, so analyzing, what are the elements of an argument? What's the sentiment? Is this positive, negative, heated, angry, sad, etc.? Recognizing speech patterns, right? So taking something that's not raw text and turning it into text. Ooh. And all kinds of stuff, all different ways of simplifying or rewriting or anything else along the way. These are the kinds of tools that we will talk about. We won't get through all of them, but I hope it's clear how walking through that last process helps us see how you could do this in a computer, and you could use it for something fascinating. So, that's the idea we've covered here, working with text. We've seen sort of the beginnings of ways text can be chopped up into units of meaning to kickstart the process of making the computer model out of it, right? So making the computer build something out of the text in the raw sense. And this two-axis approach helps us kind of situate what kind of algorithm we're working with. On axis 1, we identify the goals of the system so we can know which corners we should cut, because we know we're going to have to cut corners because true understanding is a pipe dream. Whereas axis 2, we kind of figure out what's the character of our approach. Are we going to design it all the way through top to bottom carefully by hand, or are we going to allow a little bit of machine learning to enter in to sort of bootstrap it a little bit, give it something from the real world? Maybe both. Why not both? Sometimes there is a good reason to use both, and sometimes there's a great reason not to. So, that's the idea. I hope this setting the stage for why and how you should care about what we're going to do with processing text in the Python programming language. Yeah. So, final thought. I like to leave you with something to chew on. Where else in your life have you seen errors in machine models of language? Consider places like your phone, virtual assistants, or Google. Anything that takes your text as something other than perfectly literal, as just text, and where it has to do some kind of inference to figure it out.